let's look at example 3, which I don't know why it says continued up there at the top, but whatever. Let's see, part A, let's have you graph r equals 1 minus 2 sine theta. And when you do graph it, please know that that is an important part of setting up your bounds for integrals later. So do know that, you kind of think about what you're doing as you do it, if that makes any sense. All right, so we're expecting a limacon with an inner loop just based on the form of the equation. And then let's go ahead and plug in, the 4 corners of the unit circle. And then since this is a sine-based function, we're going to plug in kind of the over 6's in each quadrant. So starting with 0, if you plug 0 in, it looks like your r value would be 1. Plugging in pi over 6, we get an r value of 0. Now because r values, this is a continuous function, as your angle increases from 0 to pi over 6, your r value would gradually decrease from 1 down to 0. So you'll get kind of a curve that connects those 2 points for what would have happened between 0 and pi over 6. All right, plugging in pi over 2, we would get an r value of -1. And just like before, your r value would have gradually decreased from 0 to -1 as your angle changed from pi over 6 to pi over 2, so you'll get that little curve there filling in the gap. All right, plugging in 5 pi over 6, we get 0 again. Plugging in pi, we get 1. Plugging in 7 pi over 6, we get 2. 3 pi over 2 gives us 3 for r. And 11 pi over 6 gives us 2 for r. So filling in the rest of the outer loop. Nice. All right. Now for kind of what we were supposed to get out of the graph. For part B, let's show how to find the area of the inner loop. So the hardest part is always going to be finding the bounds. So you want to think through, when did that inner loop start? It started with the first time we got an r value of 0, and when did it stop? It stopped with the second time we got an r value of 0. So if you remember what we just did with the graph, you would be able to figure out your bounds would be from pi over 6 to 5 pi over 6. If graphing it doesn't help you with that, you could always use the move that we used in example 2, where you set up some algebra, set r equal to 0 and solve. You'd get the same results. All right, so your integral setup for part B would be that the area is 1/2 times the integral from pi over 6 to 5 pi over 6 of 1 minus 2 sine theta, which is just the rule in terms of theta for r, squared d theta. Okay, now before we started filming the video, we did work out this integral. It took us 1, 2, 3, 4, 5, 6, 7, 8, I think 8 steps, and then we got the answer. We've decided that we really wouldn't be teaching you anything new or demonstrating anything new, so we're going to go ahead and use our ... notation. And then we're just going to say when you're all done, the answer is pi minus 3 root 3 over 2 units squared. And the ... represents the 7 steps that we are just not going to demonstrate right now. All right. Moving on to part C. Part C, I do recommend that after reading the directions, you pause the video and think it out on your own. But part C asks you to find the area of the region lying between the inner and outer loops, and I totally forgot to reprint this. The directions are not going to be to find it. Instead, let's say for part C, we're just asking you to do an integral setup, but not actually evaluate the integral. So for part C, One way to do this would be to do an integral that represents the area that goes all the way from the pole to the outer loop, which would be the integral from 5 pi over 6 to, and you would go from 5 pi over 6 all the way around to here, but you'd want to call this 13 pi over 6. Of 1 minus 2 sine theta squared d theta. Now let's stop there for a second. Let's think about what that would represent. I'll show with the highlighter. From 5 pi over 6 to 13 pi over 6, notice that all of these little infinitely small sectors, they would all go all the way from the pole out to your graph. So please notice that we did just calculate that inner loop that we didn't want. We just calculated that in our answer. So to offset that, we would just need to subtract its area away from the answer that we have here. Which you could have done in an integral form, but since we just found it in part B, I hope it makes sense that you could just write it like so. I also want to talk about another common answer that I get. So another common way to do this would be to have the bounds be from 0 to 2 pi. Of the quantity 1 minus 2 sine theta. Sorry, you just wrote what I said instead of what I meant. 1 minus 2 sine theta squared d theta. Now if you stop there, if you think about literally what this will do, it will do what you ask. It will add up infinitely many, infinitely small sectors that start at the pole, starting at 0. So it would do this little upper piece here. Then it would add in from pi over 6 to 5 pi over 6, it would add in this inner loop. From 5 pi over 6 to 2 pi, it would add in, notice it would add in the inner loop again, because it would always go from the pole out to your outer edge. So in order to get what you really wanted, you would actually need to subtract off the area of the inner loop twice. There we go. All right, that's example 3. I hope that makes sense. Take care, everybody.